Since the dawn of human consciousness, when the first hominids raised their eyes from the terrestrial plane to the celestial canopy, the night sky has presented a fundamental paradox. To the observer standing on the surface of the earth, the environment is defined by sensory experience. The warmth of a fire, the chill of the wind, the humidity of the air, and the tactile solidity of the ground. Yet, looking upward, one is confronted by an abyss of infinite depth, a canvas of absolute darkness punctured only by the cold, distant scintillation of stars. For millennia, the nature of this darkness was the subject of profound speculation. Was it a physical ceiling? Was it a fluid? Was it a void? The answers to these questions would eventually reveal that the cosmos is not merely a visual backdrop, but a physical environment of extreme hostility, defined primarily by its relationship with heat and the lack thereof. The history of understanding the temperature of space is inextricably linked to the history of understanding space itself as a vacuum. In the classical era, and indeed for centuries thereafter, the prevailing philosophical doctrine was dictated by Aristotelian physics. Aristotle, whose thoughts dominated European intellectualism for nearly 2,000 years, posited that nature abhors a vacuum, horror vacui. In this worldview, it was metaphysically impossible for empty space to exist. Every point in the universe, from the ground we walk on to the spheres of the planets, was assumed to be filled with matter. If not earth, water, air, or fire, then it must be filled with the aether, a divine, weightless, and perfect substance that facilitated the movement of celestial bodies. Because the concept of a true void was rejected, the concept of cosmic cold could not be properly formulated. If space were filled with aether, it likely possessed qualities of the divine, eternal, unchanging, and perhaps warm with the fire of creation. The night sky was not seen as a freezing abyss, but as a dense, occupied medium. It was only with the decline of Aristotelian dominance and the rise of the experimental method in the 17th century that humanity began to peel back the layers of this misconception. The realization that space is a vacuum was the necessary precursor to understanding why space is cold. The pivotal moment arrived in 1644 in Florence, Italy, with the experiments of Evangelista Torricelli. A student of Galileo, Torricelli was investigating the limitations of suction pumps, which could only raise water to a height of about 10 meters. To study this, he substituted water with mercury, a substance 14 times denser. He filled a glass tube, sealed at one end with mercury, and inverted it into a basin, also containing mercury. The column of liquid fell, settling at a height of approximately 76 centimeters, leaving a clear space at the top of the sealed tube. This space was the subject of intense controversy. It contained no mercury. It contained no air, for the air could not enter through the mercury seal. It was, for the first time in recorded history, a man-made vacuum. Torricelli had proven that we live at the bottom of an ocean of air, and that the weight of this atmosphere presses down upon us. But more importantly for our subject, he demonstrated that above this atmosphere there is nothing, no air, no pressure, no matter. This realization that the earth is enveloped in a thin, fragile layer of gas, beyond which lies a vast emptiness, fundamentally shifted the perception of the cosmos. If there is no air in space, what occupies that void? Later in the 17th century, the Anglo-Irish chemist and physicist Robert Boyle expanded upon Torricelli's work by constructing the air pump, a device capable of evacuating air from a sealed vessel. Boyle's experiments were methodical, and to the modern sensibility, somewhat macabre, yet they were essential for defining the physical properties of the vacuum. Boyle placed a burning candle inside his vacuum chamber and pumped out the air. The flame flickered and died. This demonstrated that fire, the primary source of heat and light for humanity, could not exist in a vacuum. He placed a ringing bell inside the jar. As the air was removed, the sound grew fainter until it vanished completely, proving that sound requires a medium to travel. The void was silent. Most significantly, Boyle observed the effects of vacuum on living organisms. Small animals placed in the chamber gasped and perished. The vacuum was not merely empty, it was antithetical to life. It was an environment where the fundamental processes of biology and combustion ceased to function. These experiments established the vacuum as a place of deprivation. In a vacuum, there is no air to breathe, no medium to carry sound, and no oxygen to sustain fire. But the question of temperature remained more elusive. Does a vacuum have a temperature? In the 17th and 18th centuries, the understanding of heat was still primitive. Heat was often thought of as a fluid called caloric that flowed between bodies. It was not until the development of thermodynamics and the kinetic theory of gases in the 19th century that physicists understood heat as the kinetic energy of vibrating atoms and molecules. This definition creates a linguistic and physical paradox when applied to space. Temperature is a measure of the average speed of particles in a substance. In a perfect vacuum, there are no particles. Therefore, philosophically and mathematically, a perfect vacuum has no temperature. It is neither hot nor cold. It is simply null. However, space is not a perfect vacuum. It is an extremely low-density environment, but it is populated by photons, cosmic rays, and sparse hydrogen atoms. Furthermore, any object placed in space, such as a planet, a rock, or a human body, is made of matter and therefore possesses temperature. The question then shifts from what is the temperature of the vacuum to what happens to the thermal energy of an object placed in a vacuum. To understand this, we must look to the mechanisms of heat transfer, codified by physicists like James Clerk Maxwell. On Earth, heat moves in three ways. The first is conduction, direct contact between objects where vibrating molecules bump into their neighbors, transferring energy. If you touch a block of ice, heat flows from your hand to the ice via conduction. The second is convection, the bulk movement of fluids. Warm air rises, cool air sinks, creating currents that carry heat away. This is how a radiator warms a room or how a breeze cools your skin. In the vacuum of space, both conduction and convection are impossible. There is no air to carry heat away via convection. There are no surrounding objects to touch for conduction. An object in space is thermally isolated from a material standpoint. If space were purely about conduction and convection, a hot object would stay hot forever, like coffee in a perfect thermos. But we know space is cold. This brings us to the third mechanism, radiation. Radiation is the emission of energy in the form of electromagnetic waves. Every object in the universe that is above absolute zero emits thermal radiation. The hotter the object, the more energy it radiates. Our bodies radiate heat in the infrared spectrum. The sun radiates heat in the visible and ultraviolet spectrums. Radiation requires no medium. It travels perfectly through the vacuum of space. This is the key to the cold of space. It is not that the vacuum sucks heat out of a body like cold water does. Rather, it is that a body in space constantly radiates its internal energy out into the void in the form of infrared light, while receiving very little energy in return. This process is slow compared to the convective cooling we experience on Earth. If you stepped out into a winter storm on Earth, the wind would strip heat from your body rapidly. In space, without air, you would not feel that immediate biting freeze. Instead, you would slowly, inexorably radiate your warmth away until you reached thermal equilibrium with your surroundings. But what are those surroundings? In the late 18th century, the astronomer William Herschel, famous for discovering the planet Uranus, conducted experiments that bridged the gap between light and heat by passing sunlight through a prism and placing thermometers in the various colors of the spectrum. Herschel discovered that the temperature rose even beyond the red end of the spectrum, where no light was visible. He had discovered infrared radiation, below red. This confirmed that heat travels through space as light. This leads to the extreme thermal duality of the space environment. Because there is no atmosphere to scatter or insulate heat, the temperature of an object depends entirely on its position relative to a radiation source, primarily the sun. Consider an object in Earth's orbit. The side facing the sun is bombarded by unfiltered solar radiation. Without an atmosphere to attenuate this energy, the surface temperature can skyrocket to over 120 degrees Celsius, hotter than boiling water. Conversely, the side of the object facing away from the sun, looking out into the deep void, is radiating its heat away into nothingness. That side can plunge to minus 150 degrees Celsius or lower. Thus, a spacecraft or an astronaut exists on the razor's edge between a blast furnace and a deep freeze. There is no temperate middle ground, no ambient air to mix the hot and the cold into a comfortable average. This is the thermal reality of the solar system. Extreme contrast. However, if we move far away from the sun, far away from any star, into the deepest reaches of intergalactic space, does the temperature drop to absolute zero? Absolute zero, minus 273.15 degrees Celsius, is the theoretical point where all molecular motion stops. For a long time, it was assumed that deep space might be at absolute zero. But in the 20th century, the developing theories of cosmology suggested otherwise. The universe began, according to the Standard Model, with the Big Bang, an event of infinite density and infinite heat. As the universe expanded, it cooled. The light from that primordial fireball stretched out, shifting from high-energy gamma rays into visible light, and eventually, as the universe grew vast and ancient, into microwaves. In the mid-20th century, physicists George Gamow, Ralph Alpher, and Robert Herman predicted that a background radiation should still fill the cosmos, a fossil of the first light. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn antenna at Bell Labs in New Jersey. They were plagued by a persistent background noise, a static hiss that came from every direction in the sky, day and night. They ruled out urban interference, radar, and even cleaned pigeon droppings from the antenna, thinking the dielectric material might be causing the noise. But the hiss remained. They had stumbled upon the cosmic microwave background. This radiation corresponds to a temperature of approximately 2.7 Kelvin, or minus 270.45 degrees Celsius. This is the baseline temperature of the universe. It is the floor of the cosmos. Even in the most remote void, billions of light years from the nearest star, you can never get colder than 2.7 Kelvin, because the universe itself is bathing you in this faint, ancient afterglow of creation. This is the true cold of space, a pervasive, isotropic relic of the beginning of time. The transition from theoretical physics to practical engineering began in the mid-20th century with the dawn of the space age. On October 4, 1957, the Soviet Union launched Sputnik 1. It was a simple polished sphere with 4 antennae, but its existence marked the first time humanity had to engineer an object to survive the thermal extremes of the vacuum for an extended period. The engineers faced a critical problem. The electronics inside Sputnik generated heat, and the sun heated the shell, but the vacuum insulated it like a thermos. If the heat could not escape, the satellite would cook itself. Conversely, when it passed into the Earth's shadow, it risked freezing. The solution involved manipulating the radiative properties of the satellite's surface. By polishing the sphere, they controlled its reflectivity. Furthermore, the satellite was filled with pressurized nitrogen gas. A fan circulated this gas, acting as an internal convection system to distribute heat evenly from the hot electronics to the cool metal shell, which could then radiate the excess energy into space. This was the birth of spacecraft thermal control. 4 years later, in 1961, the stakes were raised infinitely higher. Yuri Gagarin was to become the first human to enter this environment. The Vostok spacecraft was not just a machine, it was a life support system. The human body is a fragile engine that operates within a very narrow thermal range. A variance of just a few degrees in core body temperature leads to hypothermia or heat stroke. In the vacuum, where the exterior skin of the craft could fluctuate by hundreds of degrees, maintaining an internal shirt-sleeve environment of roughly 20 degrees Celsius was a monumental engineering challenge. Gagarin's capsule utilized a complex system of radiative shutters, louvers that could open and close to expose or cover a radiator surface, varying the amount of heat dumped into space. The spacecraft was also coated in specific thermal blankets to insulate it. The success of Vostok proved that a microenvironment of Earth-like conditions could be sustained within a metal shell, surrounded by the hostility of the void. There is a persistent myth in popular culture, often perpetuated by cinema, regarding the fate of a human body exposed directly to the vacuum of space without a spacesuit. The image is often one of instantaneous freezing, a person turning into a solid block of ice the moment the airlock opens. This is scientifically incorrect. As we have established, vacuum is a supreme insulator. Without air to conduct heat away, a human body would not freeze instantly. If an astronaut were cast adrift without a suit, the immediate threat would not be the cold. The first phenomenon would be the expansion of gases. The air in the lungs would expand violently. If the breath were held, the lungs would rupture. Simultaneously, the reduction in pressure would lower the boiling point of bodily fluids. Saliva on the tongue and moisture in the eyes and nose would begin to boil at body temperature. This is known as ebullition. The oxygen would diffuse out of the blood back into the lungs, leading to hypoxia. Consciousness would be lost in approximately 15 seconds. However, the thermal process would be slow. The body would continue to radiate heat into the 2.7 Kelvin background, but because the human body is largely water and possesses significant thermal mass, it would take many hours to freeze solid. The cold of space is a slow, silent killer, not the instant shatter freeze of Hollywood movies. The body would eventually desiccate and freeze, drifting as a preserved statue, but the cause of death would be asphyxiation, not hypothermia. The pinnacle of thermal engineering in the early space age was the Apollo program. Landing men on the moon presented thermal challenges far exceeding those of low Earth orbit. The moon has no atmosphere to distribute heat. The lunar day lasts for 14 Earth days, baking the surface to temperatures of 130 degrees Celsius. The lunar night is equally long, plunging the surface to -170 degrees. Apollo astronauts had to perform extravehicular activities on this baking surface. The Apollo spacesuit, the A7L, was a marvel of thermodynamics. It was not merely a suit of clothes, it was a personal spacecraft. To combat the intense solar radiation, the outer layer was made of beta cloth, a fireproof silica fiber, and coated with Teflon. Beneath this were alternating layers of aluminized mylar and captain, separated by mesh netting. This acted as a superinsulation, creating a barrier to radiative heat transfer so effective that the heat of the sun could not penetrate to the astronaut's skin, and the astronaut's body heat could not escape uncontrollably. However, the astronaut inside was working hard. Metabolic activity generates significant heat. In a vacuum, sweating does not cool you effectively because the sweat cannot evaporate into air. This was a mesh underwear woven with a network of flexible tubing. Cool water was pumped through these tubes, conducting heat directly away from the astronaut's skin. The heated water flowed to a backpack unit called the PLSS. Here, the genius of the engineering relied on the physics of the vacuum. The system used a sublimator. A porous plate was exposed to the vacuum of space. Water was fed onto this plate where it instantly turned to ice. As the warm water from the suit circulated past this ice, the heat caused the ice to sublime, to turn directly from solid to gas, skipping the liquid phase. This sublimation absorbed a massive amount of energy, cooling the circulating water, which was then pumped back to the suit. The resulting steam was vented into space. Thus, the astronauts were cooled by the very vacuum that threatened them, using the physics of phase change to survive on the surface of an alien world. This mastery of thermal dynamics allowed Neil Armstrong and Buzz Aldrin to walk on the Sea of Tranquility. When Armstrong spoke of a giant leap for mankind, he was standing in an environment of absolute hostility, protected only by a few millimeters of fabric and the laws of physics applied by engineers. The contrast was stark. Outside the suit, the lunar rocks were baking in the unmitigated glare of the sun. Inside the suit, a human being breathed oxygen at a comfortable temperature, listening to the hum of a pump circulating water. As we look to the future of space exploration, the challenge of the cold remains a primary antagonist. The James Webb Space Telescope, launched in 2021, operates on a principle that requires it to be colder than almost anything else in the solar system. Designed to observe the infrared light from the very first stars and galaxies formed after the Big Bang, the telescope's own heat must not interfere with its sensors. To achieve this, the James Webb is positioned at the Lagrange point 2, a gravitationally stable point 1.5 million kilometers from Earth, keeping the Earth and Sun permanently on one side. It is equipped with a sunshield the size of a tennis court, made of 5 layers of captain, each thinner than a human hair and separated by a vacuum gap. This shield blocks the solar energy. On the hot side, the shield reaches temperatures of 85 degrees Celsius. On the cold side, where the mirrors and instruments reside, the temperature drops to -233 degrees Celsius, less than 50 degrees above absolute zero. This passive cooling allows the telescope to peer back in time, detecting the faint heat signatures of the early universe. For future manned missions to Mars, the thermal challenges will evolve. Mars has a thin atmosphere, primarily carbon dioxide, which provides a slight greenhouse effect, but not enough to make it habitable. Temperatures on Mars can reach a pleasant 20 degrees Celsius at the equator during the day, but plummet to -75 degrees or lower at night. Colonists will face the eternal winter of the red planet. Their habitats will need to be masterworks of insulation and energy efficiency. They will not be able to rely on the thick blanket of air that protects Earth. Every structure, every vehicle, every suit will need to manage the flow of heat with precision. As humanity reaches further into the dark, venturing toward the outer planets and eventually to the stars, the cold becomes more profound. In the interstellar medium, far from the warmth of any sun, the temperature is dominated solely by the cosmic microwave background. A spaceship traveling between stars would need to generate its own heat for centuries. The energy required to keep a crew warm against the absolute indifference of the 2.7 Kelvin void is a reminder of how rare and precious thermal energy is in the universe. In conclusion, the story of the cold in space is not merely a collection of temperature readings. It is a narrative of human discovery. It began with the mythological fear of the dark, evolved through the philosophical acceptance of the vacuum, and matured into the scientific mastery of thermodynamics. We learned that space is not cold because it has a low temperature in the way a block of ice does, but because it is a vast, empty sink for radiation. It is a place where heat is a fleeting resource, constantly escaping into the infinite. The stars, those bright points of light that fascinated our ancestors, are islands of energy in a sea of entropy. They fight a losing battle against the cold, burning their fuel to push back the darkness for a few billion years before they, too, succumb and fade. For life to exist in this universe, it must cling to these sources of heat, or learn to carry its fire with it. The history of space exploration is the history of carrying that fire, first in the form of understanding, then in the form of technology, into the great, silent cold. From Torricelli's mercury tube to the liquid-cooled suits of Apollo, we have learned that while the universe may be indifferent to our need for warmth, our ingenuity allows us to endure. We have learned to survive in the void, to navigate the thermal extremes, and to look into the freezing darkness not with fear, but with the calculated curiosity of a species determined to understand its place in the cosmos. The cold is absolute, but so is the human drive to explore it.